Hello, good evening, everyone. Okay, so in today's meeting, we're going to discuss how to apply yung Schrödinger wave equation sa mga iba't ibang systems. Okay, we already tried to apply the Schrödinger equation on a free electron last meeting, but this time we're going to use potential, a finite potential, or actually some potential value. Okay, we'll begin actually with an infinite well potential, and then tignan natin yung properties ng potential when tawag dito in terms of its symmetry and what happens dun sa resulting na solution dun sa Schrödinger equation as a result of this symmetry. Okay, so of course we will begin our discussion with the Schrödinger equation, with Schrödinger's equation. Okay, and we write the time-independent Schrödinger equation as okay. So oops. So H, okay, the Hamiltonian acting on the wave function, okay, psi sub n r, okay, equal to negative h bar squared over 2m, okay, del squared plus vr. Okay, ito yung ating Hamiltonian. Okay, and then operating on psi n of r equal to yung psi sub n of r. Okay, recall na ang tawag natin dito sa psi of n ay eigenfunctions. Or eigenstates. Okay, at itong E sub n ay tinatawag natin eigenvalues. Okay, yung E sub n, na-derive din natin yun before, to have values equal to h bar omega sub n. Okay. And then yung psi sub n, yung eigenstates, was derived, okay, from the time-dependent wave function, okay, by doing a separation of variables. Okay. So yung psi sub nr na eigenstate, okay, is just, or psi sub nr of t na eigenstate is just a product of two terms. Yung psi sub nr, yung time-independent na wave function, and then yung time-dependent na component ng wave function. Okay. Ang tawag natin dito sa psi sub n na ito, okay, ay time-independent stationary states. Tinatawag sila na stationary states, well, particularly because time independent nga sila. Okay, yung tawag dito, pag hinanap natin yung probability density, di ba? Nung psi sub nr of t, okay, we actually end up with psi sub n r. Okay, kasi itong term na ito, okay, ay nawawala, okay, when we do a probability density, or they cancel out. Okay, so kaya natin sila tinatawag na time-independent stationary states. Okay, of course, they're not really stationary states in the sense na hindi sila gumagalaw. Okay, but they're actually tawag dito. And later on, actually, magko-compute nga tayo ng current, which implies that there's some motion, okay, of the electron dun sa space na ginagalawan niya. Okay, ang ibig sabihin lang nitong stationary state is that meron siyang isang state na bound as a result of the potential, and because of this because this electron is bound within a specific region, okay, yung propagation, okay, nung electron, okay, ay nagka-cancel out, okay, due to yung reflection niya of the walls of the tawag dito, of the potential, okay, due to the potential barrier. Okay, you can think of it as this way. So sa 103 meron kayong mga waves, okay, na tawag dito, pag inallow niyo na mag-propagate yung wave to the pag pinallow niyo yung mag-propagate yung wave from the right to the left, okay, dun sa end, okay, pag yung string niyo ay okay, ulitin ko. So meron kayong string, okay, tapos mag-allow kayo ng wave na mag-propagate to sa string na yun from one direction to the other. Okay, and then since yung ends ng string ay tawag dito bound, okay, so ano siya, hindi siya loose, okay, ang mangyayari dun sa wave na yun ay babalik siya, okay, and and then pagpunta niya dun sa kabilang side, magre-reflect ulit siya, and so on and so forth. And as a result, magkakaroon kayo ngayon ng waves that is traveling in one direction, another wave that's traveling in opposite direction. Okay, and mangyayari dyan is they will interfere, and they will create standing waves. So you see these standing waves dun sa dun sa string na yan as a wave na parang stationary. In the same sense, we have this in quantum physics. Okay, na meron kang current propagating in one direction, and because of the potential barrier, you have a wave that will be reflected off the barrier and will travel in the opposite direction. And then you'll create these standing waves. Okay, but it's a little bit, it's slightly a little bit more complex than that compared dun sa standing waves na na-form dun sa string. And we'll learn about it in a little while. Okay, now the thing about quantum physics is, tulad ng sinabi ko sa inyo last time, itong equation na ito, okay, is the equivalent equation. Okay, is the go-to equation pagdating sa quantum physics. Sa classical mechanics, you have Newton's laws. Pagdating sa quantum physics, you have Schrödinger's equation. Yan parati yung starting point. Okay, and depende kung ano yung physical system niyo, okay, yung potential na ilalagay niyo dyan. So the potential actually describes the physical system. Okay, so for example, dun sa dinescribe natin last time, okay, meron kang free electron. Okay, and since free yung electron, it doesn't experience any potential. Yung potential ay zero. As I discuss natin this meeting, yung potential na gagamitin natin is an infinite barrier potential. So meron kang infinite potential outside a specific region, and inside the specific region, zero yung potential. Okay, makikita natin mamaya yung itsura ng potential na yan. Okay, and then you have other types of potential like yung finite barrier potential, harmonic oscillator na kung saan yung potential ay parabolic. Okay, and then more complicated potential, depende kung ano nga yung physical system na gusto niyong pag-aralan. Okay, and basically ganyan yung fundamentally ganyan yung paggamit ng Schrödinger equation. You start with Schrödinger equation. Okay. Okay. And the only change that you're going to do is to change the potential. Okay. And then you solve the differential equation. Okay. There are some potentials that are easy to solve. there are some potentials that are symmetric and makes it easier to solve. Okay? And of course, may mga potential na medyo komplikado na. Okay. They're a little bit harder to solve pero solvable pa rin. And then may mga potentials na hindi na kayang i-solve dahil sa complexity ng differential equation. So hindi straightforward yung pag-solve. Like yung three-body problem, for example. Okay, so dito sa course na ito, sa 181, we're going to look at potentials na madaling ma-solve, and then we're going to look at how to solve them both numerically and also by solving the differential equation analytically. Okay, so yan na basically yung gagawin niyo sa quantum physics. Ano yung potential ng system? At pag naintindihan nyo na kung ano yung potential system, i-plug in yung Schrödinger equation and then you solve the differential equation. Okay, yun na yung ginagawa before at yun pa rin yung ginagawa hanggang ngayon. Okay. Now, before we proceed with the discussion of the potential, okay, tignan muna natin yung nature ng wave function. Okay, dapat we impose na yung wave function, okay, and yung kanyang derivative, okay, must be ay dapat continuous. Okay, now I'm writing here the wave function in one dimension tsaka yung derivative in one dimension only because yung derivation na gagawin natin is easier to do in one dimension. Pero regardless kung ilang dimensions yung pinag-aaralan, the wave function and its first derivative, okay, must be continuous. Okay, anong implication nun pag hindi continuous yung wave function? So tignan natin dito yung wave function. Okay, yung figure specifically. At this position, so itong position na ito is x naught. Okay, so pag i-extend natin itong graph na ito, yung position na yan is x naught. And at x naught, merong discontinuity. Okay, yung line na nakikita niyo dyan is not really a line that connects the two graphs, but instead it's just a descriptive na line. So when you approach psi of x from the left, ito yung magiging value nung psi of x naught. Okay, yung point na yan, yung value ng psi of x naught if x is approaching x naught from the left, and ito naman yung magiging value ng psi of x naught if x is approaching x naught from the right. Okay. So from the right, ibig sabihin dito siya nag-approach towards the left. Yan yung value. So makikita niyo na discontinuous siya at x naught. Magkaiba yung value ng psi of x naught dito at saka yung value ng psi of x naught dito. Yan yung discontinuity. Okay, now yung problem kasi dyan is that yung kinetic energy dito ay infinite if you have that discontinuity at x naught. And we can show that, okay, by starting with this equation. So let's consider yung expectation value ng kinetic energy. Okay, so yung T dito is kinetic energy, and we know that kinetic energy is just P squared over 2m. Okay, and natutunan na natin na yung P squared is an operator, di ba? Yung P specifically is an operator, negative IH bar ddx sa quantum physics. Okay? Okay, so we can write this ngayon as equal to negative h bar squared over 2m, okay, integral, okay, ng psi star Okay, d squared dx squared psi dx. Okay, so what this means is that we're looking at yung difference ng expectation value dito and yung expectation value dito ng kinetic energy. So this represents delta of the expectation value of T. Okay? Yung difference na yan. Okay. Furthermore, kung tataka kayo kung saan galing itong mga to, remember that the expectation value of an operator is written as psi star operator psi dx. Okay, and in this case, yung operator ay yung A. So ito yung operator, yung kinetic energy, and yung operator na P squared is written as this. Okay, so kaya meron ganyan. Kaya ganyan siya nakasulat. Okay. Now, ano yung limits of integration natin dito? Okay, to determine yung limits of integration, okay, we need to approach x naught from one side, okay, dito. So the lower limit ngayon is x naught, okay, and then we introduce a dummy variable 1 over eta. Okay, and then doon naman sa taas, so dito, okay, dito, we're going to introduce a dummy variable 1 over eta. Okay, x naught plus 1 over eta. Okay, so ang ginagawa ng eta dyan is if we take the limit as eta approaches 0, sorry, eta approaches infinity, okay, then we're essentially allowing, so itong lower limit, we're allowing eta to approach x naught in this direction. And then yung upper limit is we're allowing eta to approach in this direction. Kasi di ba, as 8 approaches infinity, then 1 over 8 approaches 0. So both yung lower limit at saka yung upper limit ay nag-approach ng x naught. Okay? Okay. So then we can rewrite this ngayon as using integration, using ang tawag dito, integration by parts. Okay, so if we say na, if we let u be equal to psi star, okay, and v prime be equal to d squared dx squared psi dx. Okay, then ibig sabihin ang du is equal to d dx psi star, and then ang v ay equal sa first derivative ng psi. Okay, d psi of psi. Okay, so yung delta ng expectation value ng kinetic energy is then written as, okay, negative h bar squared over 2m, then you take the limit as eta approaches infinity, okay, and then you have uv, okay, psi star d dx psi, okay, and then evaluated from the limits of integration of x naught minus 1 over eta, and then x naught plus 1 over eta minus, okay, and then yung integral ng v, okay, du. Okay, ito yung v, and then ito yung du. Okay, and so that's just d psi star dx and then d psi, so modulus yan, di ba? Squared and then dx. So x naught minus 1 over eta, and then x naught plus 1 over eta yung limits of integration. Okay, of course, now we need to evaluate yung yung, integrals na ito. Okay, so let's evaluate this term first. Okay, and we're going to use maybe a theorem na hindi familiar sa inyo. Okay, so I'm just going to add one, okay, one slide. Okay, and the theorem is called the median value theorem. It's a mathematical theorem, okay, for functions f of x and g of x, okay, which states na if you have a function, if you have an integral of f of x, g of x, dx evaluated from a to b, you can write it as f of psi, okay, okay, and integral from a to b ng g of x dx, okay, where a is less than psi, less than b, with f of x is equal to g of x is equal to d psi of x dx, okay? So yung integral, yung second integral dito, okay, we just write it here. Okay, from x naught minus 1 over eta, x naught plus 1 over eta ng dx squared, okay, dx is equal to, okay, so pareho lang naman sila, diba? So we can write d psi of x dx, okay, and then note na yung f of x in-evaluate at x equals psi. So we evaluate x at yung value na psi. Okay, and then yung limits of integration x minus 1 over eta, x naught plus 1 over eta. Okay, and d psi dx. Dx. Okay? Okay, so anong makukuha natin dito ngayon? We get d psi dx, x evaluated at psi, and then of course, we evaluate itong ano na to. Tawag dito, itong integral nito. Magka-cancel yan. So we'll have integral ng d psi, which is just psi, and then evaluated at yung upper limit of integration, and then yung lower limit of integration. Okay. Okay. And dapat this is satisfied. So dapat yung lower limit x naught minus 1 over eta yung psi na dummy variable, yung psi dito sa median value theorem, it must be between yung lower tsaka upper limit ng limits of integration. Okay, so anong makukuha natin dito ngayon? So remember that we're taking the limit as n approaches infinity, which means na if you take the limit as n approaches, as not n but eta approaches infinity, then this limits of integration actually approaches eta. But dito sa figure, if we allow eta to approach infinity, it also approaches x naught. So this means na itong x na ito actually approaches, itong x na nandito actually approaches x naught. So we can write this. So so this is actually the same as x equals x naught. So we can evaluate the derivative at x equals x naught, okay, which is just which is which is actually infinite, diba? So upon evaluating x equals x naught, ito becomes infinite. Okay, bakit siya magiging infinite? Okay, kasi if you take a look at this, okay, ito yung d psi. Okay. Well, actually, ano ba ang d psi dx? Ang d psi dx is the slope, okay, of the tawag dito, tangent line at a particular point. But here we have this line, okay, that connects these 2 points. So essentially, yun yung tangent line ninyo. And makikita natin that the line is 90 degrees, which means na yung derivative na yan is infinite. Okay, this will have a finite value. Okay, if you take the limit as eta approaches infinity, then this will simply approach psi of x naught dun sa left, and then psi of x naught to the right. So meron lang siyang finite na value corresponding to yung difference ng psi of x naught dito. Okay. So ang gusto nating sabihin dito is, okay, if we go back to this equation, okay, this integral here becomes infinite. Okay, when we take the limit as eta approaches infinity, which means that this approaches infinity. So yung change in kinetic energy approaches infinity. Now, physically, that doesn't make any sense, di ba? Kasi saan kukunin nung particle yung energy na yan? That energy has to come from somewhere. So there's no infinite energy, and we know from energy conservation na energy is finite, di ba? So this idea na yung expectation value ng change in the expectation value of the kinetic energy is infinite, it has no physical meaning. Okay, that is why yung psi of x ay kailangan na continuous. Okay. So what about yung derivative naman ito? Bakit itong derivative dapat maging continuous din? Okay, to sort of illustrate kung paano natin i-describe yung infinite na yung derivative, okay, na infinite. Kung paano natin ma-describe yung behavior, okay, pag yung derivative, okay, is discontinuous, okay, we take a look at this graph. Kung titignan natin, we extend this, no? So this is yung x ninyo. And then at this position, this is x naught. If you take the derivative of this graph, okay, which is nothing but yung slope. Okay. Actually, hindi. Sorry. Hindi ganyan yung shape ng graph. So, pag ganyan yung shape, ibig sabihin yung slope niya is 0. Dito yung derivative nito is something else. Kasi if you approach it from the right, okay, if you approach it from the left pala, then nakikita nyo na nag-increase yung slope niya, di ba? From here to here to here, nag-increase yung slope niya. And then you approach it from the right, okay, nag-increase din yung slope nito pag ganyan. So, ang nangyayari is, if you're looking at it, tawag dito, in both directions, yung slope niya ay nag-increase ng pag ganyan. Okay, so yun yung derivative. Yun yung description natin for the derivative of the wave function. Okay, our approach will be similar as doon sa ginawa natin sa psi na function. So we take the expectation value, the kinetic energy. So yun pa rin yung starting point natin. Okay, and this will be the limit as eta approaches infinity. Okay. So yung naging solution natin kanina ay psi d psi dx x naught minus 1 over eta x naught plus 1 over eta. This is after the integration by parts. So minus integral from x naught minus 1 over eta x naught plus 1 over eta. Okay, and then d psi dx squared dx. Okay. Now, at this point, alam na natin na yung psi of x is continuous. Okay, kasi na-derive natin, pinakita natin na dapat continuous siya from our derivation. Okay, and d psi dx has finite values everywhere. Okay, so since psi of x is continuous, then d psi dx has finite values. Okay, everywhere. Okay. So we know na ngayon, itong integral na to will have a finite value. Okay. So yun yung dinidescribe ko kanina na ito, if you're coming from the left, then yung slope, okay, has finite values everywhere. If you're coming from the right, they have finite values everywhere. And as you approach x naught, or as you take the limit as eta approaches infinity, so you're approaching x naught, then finite pa rin yung values niya. Okay, so that means that yung integral to has finite values. So we are left with this first term. Okay, yung first term na yan. So now we evaluate this limits of integration. So now we have psi of x naught plus 1 over eta. Psi prime is the derivative, no? X naught plus 1 over eta minus, so may limit pa rin dito as eta approaches infinity. Okay. And then psi x naught minus 1 over eta psi prime x naught plus minus 1 over eta. Okay, and alam natin na as eta approaches infinity, okay, then yung psi of x naught plus 1 over eta is equal to psi of x naught minus 1 over eta is equal to psi of x naught. Okay, equal na sila. Kasi nga sinabi natin na psi of x is continuous. Okay? Remember, kung hindi sila continuous, then psi of x naught dito at psi of x naught dito ay hindi pareho. Pero dahil sinabi natin na continuous na yung function na ito, okay, yung function na nandito is continuous na, then yung psi of x naught plus 1 over eta approaching, so that's approaching from the right, and then psi of x naught minus 1 over eta approaching from the left will be equal to the same value, psi of x naught. Okay. Ang problema na lang natin, so ibig sabihin pwede na natin i-factor out ito at saka ito kasi pareho lang naman sila. So ang matitira sa loob is, sa loob ng square brackets is itong difference na ito. Okay, so we can write that as delta psi. So delta psi is equal to psi prime x naught plus 1 over eta minus psi prime x naught minus 1 over eta. Okay. Which means na yung delta ng expectation value ng kinetic energy can be written as negative h bar squared over 2m psi of x naught. Okay, ito yung finactor out natin, yung psi of x naught. And then delta of psi. Where delta of psi is this one. Okay, now anong ibig sabihin nito? Okay, so we have tawag dito, an expectation value or a difference in expectation value that is proportional, okay, to the difference in the slopes, okay, of the wave function at x naught. Okay, if you take the limit as eta approaches infinity, then this is just psi prime of x that approaching from different sides. Pero nakita natin na may finite na value siya. Okay, which means na yung change or yung difference in kinetic energy, difference in the expectation value of the kinetic energy also has a finite value. Ano ang physical interpretation for this? Ibig sabihin, yung kinetic energy na ito, this constitutes as additional kinetic energy. Okay. Remember, this is a difference between yung actual na kinetic energies. Okay? So you're expecting just one kinetic energy, but instead you have parang dalawang kinetic energies or added to yung kinetic energy na ina-expect natin. Okay? Which means na, anong tawag dito, depende sa value or depende sa psi, okay, pwede kang magdagdag ng kinetic energy. And kailan ba sa classical physics tayo nagdaragdag ng kinetic energy? Okay? Walang chance na gano'n. We only do that sa tawag dito sa potential energy. Potential energy is arbitrary. Okay? Pwede mong iset yung isang position na may potential na 0 and then you relate everything, you relate the potential of everything else from that reference position. Pero sa kinetic energy at a particular position, may value na talaga yung kinetic energy niyan and you don't add anything else to that. Wala kang nilalagay na arbitrary value. So again, although it sounds that it's physically possible, okay, yung pag-add ng energy, okay, yung pag-add ng energy sa kinetic energy, okay, doesn't really make sense kasi yung kinetic energy ay hindi arbitrary. Okay? So that's why we impose, okay, na yung derivative ng psi with respect to x must also be continuous. Okay? Now, itong concept na ito na continuity ng psi of x tsaka ng d psi of x, okay, ay gagamitin natin, okay, pag nagsosolve na tayo ng Schrödinger equation and we apply the boundary conditions, okay, dun sa system. Okay? Okay, so now that we have that condition imposed for the wave function and its first derivative, okay, we also discuss a few more conditions. Okay, so for example, yung wave function, so you have this, I don't know, Schrödinger equation, so negative h bar squared over 2m del squared plus br, okay, psi of nr is equal to e sub n psi of nr. So yung wave function na yan, they're also orthogonal and normalized. Okay. Of course, normalization comes from tawag dito yung property ng normalization comes from yung normalization ng wave function na dinescribe natin from last meeting. Okay. So sa mathematical physics, ang tawag natin dito ay orthonormal, okay, condition. And may equation tayo na ginagamit for that. Okay. So that's psi, okay, psi n star of r, and then psi m of r, d3 r. Okay, at ito ay equal sa Kronecker delta nm. Okay, kung saan yung Kronecker delta nm is equal to 1 if n is equal to m and 0 otherwise. Okay. Furthermore, So ito yung unang condition, no? Furthermore, yung orthogonal wave functions na ito are complete. Okay? So that any arbitrary wave function can be expressed as a sum of orthonormal functions. Normal wave functions. Okay, weighted by coefficients. Okay, A sub n. Mathematical form, you write this as sum over n ng A sub n psi of n of R. Sorry. Hindi ito psi of n. So yung completeness ng wave function. So ito yung complete na wave function at ito yung individual na wave function. So they are superposition of states. So ina-add natin lahat ng wave function na yan sa isa't isa. Okay? And then each of the wave function has a weighing parameter. It has a weighing coefficient. Okay? We'll understand this better, okay, later when we start to begin or when we start to discuss mga examples. Okay, yung A sub n na yan leads to yung probability, okay, na kung saan yung particular na state, okay, ay makikita. Okay. So briefly, siguro, this is the equation, okay, that actually describes yung Schrödinger's cat na behavior. Okay. Pag sinabing, kung naalala niyo yung kwento ng Schrödinger's cat, you have a cat inside a box, okay, na dun sa loob ng box ay meron ding vial of poison. But you have no idea whether the cat is alive or dead kasi hindi nyo rin alam kung yung vial ng poison ay na-break open or hindi. Diba? So the only way to take a look at that is, the only way to know is to look at that. And that's measuring. That's a way of measuring. So if you open a box, you measure yung state ng system. Now, before you open the box, kumpleto yung lahat ng states. Ano yung mga states? Dalawa lang. Cat is alive and the cat is dead. And merong weight yung yung bawat state na yon. In this case, yung weight ng isa is 1 over square root of 2 at yung weight ng pangalawa is 1 over square root of 2. You understand kung bakit 1 over square root of 2 maya-mayang konti. Okay? Then, once you make a measurement, okay, ibig sabihin, bubuksan mo yung box na yon, then you push yung state na yon towards one specific tawag dito, one specific situation. Okay? Pagtingin mo, nakita mo na, okay, tawag dito, buhay yung pusa. Okay? So that's one behavior. Okay. If we do the experiment again, so close the box. Pag sinara niyo yung box, then andyan ulit yung superposition of states. Dalawa ulit yung states na present. Okay. Cat is both alive and dead. Okay. Kaya ako sinasabi na and kasi you're adding all of those states. It's a superposition of states. When you open the box, okay, makikita nyo na yung cat ay patay. Okay. So by doing a measurement, you push the state towards a specific. You push the situation towards a specific state. Diba? In this case, Doon sa second measurement, the cat is dead. And if you do that over and over again, okay, for like say 1,000 times, makikita nyo na, anong tawag dito? Eventually, magle-level, okay, yung probabilities na kung saan yung pusa ay buhay when you make a measurement or patay. Okay? And yung probability na yun is 50%. Okay? So 50%, it's either 50% dead and 50% alive. And recall na yung probability is described by, okay, the modulus squared. Okay? So if sa Schrödinger's cat, okay, you have 1 over square root of 2, the cat is alive, and 1 over square root of 2, cat is dead. Okay, and you take yung probability niyan, okay, so yung wave function ganyan, okay, then yung probability niya is 1/2 that the cat is alive plus 1/2 that the cat is dead. Okay, kaya 1 over square root of 2 yun dyan kasi yung probability is 1/2. Okay, so ganyan natin din describe yung Schrödinger's cat. We describe it with this uh, equation. Okay. 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 So now we take a look at yung potential, property ng potential. So V of R, okay. Yung V of R, tawag dito, has certain properties. Okay. Well, in some systems, okay, V of R has what it's called an inversion symmetry. Well, magdedepende yun dun sa coordinate system na ginagamit ninyo. Okay, so that's why a reference frame is, a coordinate system is really important. Okay, and ito yung mga parang tinetake for granted, di ba? Pero by choosing a correct coordinate system, then you actually will allow yung potential to become symmetric. Okay? Or you actually allow the potential to have inversion symmetry. Ano ibig sabihin ng inversion symmetry? So what this means is that if we invert yung space, that means mathematically you tawag dito, you let R be equal to negative R, or R becomes negative R. Then you end up with the same result. Okay, so graphically, in one dimension siguro, okay, in one dimension, pag tawag dito, you can think of inversion symmetry as kung ano man yung itsura niya dun sa positive x-axis. Okay, you have inversion symmetry if it results to the mirror image dun sa negative x axis. Okay, so they have the same sort of shape. Okay, then if this is the case, then yung wave function ninyo, okay, will have odd or even parity. Okay, so in other words, yung wave function will have this property. Okay, so pag positive, okay, yan yung even parity. Okay, and then pag negative, yan yung odd parity. Okay. So this should be negative R. Okay. So, isang function, okay, siguro na pwede natin consider yung may odd parity is cosine theta. Okay, kasi pag kinuha niyo yung cosine ng negative theta, they're just the same. Okay, pero yung sine theta, so this is even parity. Okay, pero pag yung sine theta, pag kinuha niyo yung sine ng negative theta, then it becomes negative sine theta. Okay, so this is yung odd na parity. Okay. Now, there are cases na kung saan yung eigenfunctions, okay, that have the same eigenvalues, okay, ay hindi nag-obey nitong ganitong klaseng parity. Okay. The only way for that to happen is if they are linearly independent. Okay. In that case, ang gagawin nyo is magko-construct kayo ng panibagong wave functions, okay, which includes pa rin itong mga original na wave functions so that they become linearly dependent. So ang ibig ko sabihin is magkakaroon kayo ng panibagong wave function that will have this form psi of r plus psi of negative r. Okay, and so ibig sabihin ito ay may even na parity. Okay, and you can easily show that, okay, that they have even parity. So psi minus is psi of r minus psi of negative r, and here we have odd na parity. Okay, so that is also something that you can do. Okay, so ang point lang dito is that when the potential has inversion symmetry, then yung wave functions, okay, yung eigenfunctions will have either even or odd parity. Okay, and it's something that you really want. Okay, kasi tawag dito, it sort of provides a solution. Okay, it sort of provides a solution that makes physical sense. Okay. Okay, so now we can show an example, okay, of a potential, okay, that has inversion symmetry. And because it has inversion symmetry, we can see that it will have even and odd parities. So dito, we have an infinite potential. Well, okay, and what this means is that yung potential na ito is infinite. Okay. Anything greater than L over 2. Okay. Yung potential, of course, is located between negative L over 2 at saka L over 2. And anything greater than L over 2, you have infinite potential. For anything less than negative L over 2, you have also infinite potential. Okay. Okay. E or equal to. Okay. Tapos, anything in between negative L over 2 at saka positive L over 2 ay zero na potential. Okay. And because the potential is infinite, okay, dito sa regions na ito, okay, the probability of finding a particle is zero. Okay. Kasi, diba, how can a particle exist in that infinite potential? Okay. Well, yun. But yun lang yung the only sensible way to answer that question is that it doesn't exist in that infinite potential. Okay, so hindi tayo nag-expect ng tawag dito ng in other words, walang probability na makita natin yung particle in that region, outside of that region. So yung consider lang natin ay between the region na negative L over 2, okay, at saka positive L over 2. So v of x is 0 in that region. which means that if we revert to our Schrödinger equation, okay, we can write it as psi of x, okay, equal to E psi of x. Okay. B of x is equal to 0. Okay. Now we have this Schrödinger equation for the infinitesimal potential. The next step, of course, is to write yung boundary conditions. So at x equals negative L over 2, okay, hindi nag-exist yung particle. So in other words, psi of x, okay, at x equals negative L over 2, okay, will be equal to, okay, may nakalimutan akong banggitin. Ano ba yung solution ng differential equation nito? So ilalagay ko muna dito. So ang solution ng differential equation na yan, okay, well, alam niyo from 1 to 1, you can have a solution which is exponential, and then you can have a solution which is also sinusoidal. Okay, for now we use an exponential solution, but makikita natin later na we can use a sinusoidal solution. Okay, so we write it as a exponential negative I kx plus b exponential positive I k x. Sorry, positive I kx and then negative I kx. Mas gusto ko lang nauna yung positive. Okay. So now we know the solution. Okay. So at x equals negative L over 2, okay, so at x equals yung negative L over 2, yung wave function natin becomes a exponential negative I k, and then papalitan natin yung x ng negative L over 2. So that's I k L over 2 plus b exponential positive I k L over 2. And then at x equals L over 2, yung wave function na yan, okay, I experiences an infinite potential. So the probability na makita niyo yung particle at that position is 0. At x equals positive L over 2, okay, yung wave function, okay, is written as exponential negative I k L over 2 plus b exponential negative I k positive I k L over 2. Anong ginagawa natin? So this actually should be negative. And that is positive. Ito naman dapat ay negative. Okay, then L over 2. And this should also be equal to 0 kasi at x greater than or equal to L over 2, yung probability na makita yung particle is 0. Okay, so that's one of the boundary conditions. Okay, now, ang idea dito is to solve for A and B para makuha yung coefficients na yan, ano? Okay, and we can do that using linear algebra. Okay, so well, we can also see na yung determinant ng coefficients. Okay, so ito exponential I KL over 2, then ito exponential I KL over 2, and exponential positive I KL over 2, and then exponential negative I KL over 2. We can now write that as exponential I KL. Okay, ito pag multiply, di ba? And then minus ito pag multiply minus exponential I KL, and of course that should be equal to 0. Yung determinant dapat nila ay 0. They are 0 kasi dapat yung coefficients na to ay linearly, yung wave functions na yun ay dapat linearly independent. Now, ano ba itong tawag dito wave function na ito? O ano ba itong difference na ito? This is actually equal to 2i sine kl. Okay, so dapat 2i sine kl is equal to 0. Or in other words, sine kl ay dapat equal to 0. Okay, now at this point, we're now going to introduce a subscript dun sa k. Okay. So sine k sub n l is equal to 0. Okay. Bakit tayo mag-introduce ng subscript? Kasi kailan ba magiging 0 yung sine k and l? 0 lang yan if k and l is equal to n pi. Okay, where n is positive non-zero integer. Okay, so k sub n ngayon is equal to n pi over L. Okay. Recall na yung wavelength. Sorry, yung wavelength ng isang wave function dito is 2L over N. Okay, madali lang naman natin ma-figure out yan. So, pwede natin ngayon i-write ito as 2 pi over lambda sub n, okay, or n, anong tawag dito? 2 pi over 2L or n pi over L, okay, which is why we have this expression for k sub nl. Okay. Okay, so n equals 1, 2, 3. Okay. So, sa classical, in other words, yung classical physics na result corresponds also dun sa result dun sa nakuha natin sa quantum physics. So, E sub n ngayon, okay, which is given by h bar squared k squared over 2m can now be written as h bar squared over 2m times n squared pi squared over L squared. Okay, so for n equals 1, then you have E1 is equal to h bar squared over 2m pi squared over L squared. So this is the lowest energy state or tinatawag natin na ground state. Okay. In some cases, this is also, or this is also what's referred to as the 0 point energy. Okay, at least for the bound state. Okay. So, ang ibig sabihin nito is there's no energy equal to 0, okay, for this system. Okay. In quantum physics, the lowest energy state is called the ground state, and it's not necessarily 0. Okay? Hindi katulad sa classical physics, okay, na kung saan pwede kang magkaroon ng zero energy, zero kinetic energy, okay, for that matter. Okay, and tawag dito, so yung n equals 2 ngayon dito is E2 is equal to h bar squared 2m times 4, diba? So this will become 2. Okay, cancel natin yung 2 dyan. Sorry. 2h bar squared over m pi squared over L squared. This is called unexcited state. So lahat ng states na sa ibabaw ng ground state ay excited state. Itong particular state na ito ay tinatawag na first excited state. Okay. Okay. Then, naragdag lang ako ng slide. Okay. So, ang next step dito, of course, is to determine kung ano yung tawag dito, kung ano yung wave function. So nakuha na natin yung ano, di ba? Nakuha na natin yung energy eigenvalues. Okay. The next step is to determine kung ano yung energy kung ano yung eigenfunctions. Okay. So E1 is equal to h bar squared over Tm, ito yung ground state, pi squared over L squared. Okay, this corresponds to the lowest energy level, okay, ground state, or h bar omega 1. Okay. And yung corresponding na ground state dito, wave function, is cosine pi over L x. Okay. E2 is equal to 4 times E1, di ba kasi n squared, right? Okay, so this will be n squared h bar squared over 2m pi squared over L squared. So n squared E1. So this is equal to h bar omega 2, and psi of 2x is equal to 2 over L square root sine pi over L times x, and then E3 is equal to 9E1 is equal to h bar omega 3. Psi of 3 is equal to 2 over L square root. Sorry, 2 pi. Dapat yan. Cosine 3 pi over L x. This has even parity. This has odd parity. And this has even parity. Okay, so you might ask kung saan nanggaling ito. Nanggaling yan by applying yung normalization condition. Okay, now I'm going to leave it to you as an exercise. In fact, you can try solving problem 3.6. Okay, dun sa problem 3.6, it's also an infinite potential well, pero shinif niya ng konti yung potential. So yung v of x equals 0 ay from 0 to L na. Okay, between 0 and L. So hindi na from negative L over 2 to L. To L. Negative L over 2 to L. Positive L over 2. Okay. Now, regardless kung shinif yung potential, okay, you still end up with the same result. Okay, what you'll have is psi of n xt is equal to a sub n psi k sub n of x. Okay, then you apply yung boundary conditions, okay, na kung saan yung psi of n at x equals 0 at yung psi of n at x equals L will be 0 because the particles particles do not exist dun sa boundary, okay, and outside boundary. Okay, and then you apply yung normalization condition. So integral from 0 to L ng psi of n x squared dx. Dapat yan ay equal sa 1. Okay, so ito, ipasok nyo lang dito and then solve for a sub n. Okay, so it's a good exercise for you to to know, okay, or to practice on. Okay, now if we graph that, okay, anong magiging result? Okay, so pag ginraph natin yung tatlong states na yun, we have this ground state dito, ito yung E1, first excited state and the second excited state. Then we have this three wave functions. So ito yung eigenfunction corresponding to the ground state. Okay, at makikita nyo kung bakit siya tawag dito even symmetry, kasi this is just a mirror image of that. Okay. Okay, now for the first excited state, psi2, ito yung magiging result. Okay, so yan. And in this boundary, so hindi siya mirror image, hindi lang siya mirror image, pero may inversion ka pa na, pag ganyan. Okay, so yun yung ibig sabihin dito ng odd parity. So to recognize that it has odd parity, okay, so meron kang reflection about this tawag dito about this point of symmetry, and then dito din meron ka ring reflection. Okay. Okay. So then yung third na eigenvalue or second excited state, eigenfunction, second excited state, okay, yung kulay pula, makikita nyo na symmetric din siya about this tawag dito, about this point. Okay, mirror image din siya. So meron siyang odd parity. Okay. Now, yung solution na ginawa natin doon is analytical. Okay. Of course, you can also solve this numerically. Okay. And this we can do by simply applying finite difference methods dun sa second order differential equation. Okay. So if we begin with the with the Schrödinger's equation. Okay. Then we have h bar squared over 2m d squared dx squared plus vx, okay, psi of x, okay, e psi of x. Okay, recall na sa finite difference, okay, yung d dx, okay, ng psi of xj is equal to psi of xj minus psi of xj minus 1. So this is the forward finite difference method, okay, divided by h naught, okay, na kung saan yung xj minus 1 is h naught. Then yung second derivative can then be written as psi of xj. Okay, psi of xj minus 1 minus 2 psi of xj plus psi of xj plus 1 all over h naught squared. Okay, so kung ngayon ililipat ko tong e dun sa kabilang side, okay. So kasi alam naman natin yung eigenstates, di ba? So or at least alamin natin yung eigenstates. So h minus e is equal to psi of x. Okay, then we have u uj psi of xj minus 1 minus, okay, dj minus e. Okay, so psi of x j minus uj plus 1 psi of xj plus 1. Okay. And then you sum overall j's hanggang sa kung ano man yung dimensions. Oops, sorry. Kung ano man yung dimensions. Okay. O kung ilang elements yung gusto mong ilagay. O ilang data points. Yung uj is equal to h bar squared over 2m h naught squared. So that's yung h bar squared over m dito. Tapos yung h naught dito or h naught squared dito. Okay, yun yung coefficients na uj. Yung dj naman is equal to h bar squared over m h naught squared plus yung dj. Okay, so yung potential at each of the step. Okay. Kasi, di ba, yung wave function nyo has sort of this, for example, this shape. Okay. Halimbawa, ganyan yung shape ng wave function. So, gagawin nyo, i-discretize nyo yan. Okay. So, ito yung h naught, di ba? Then ito yung 2h naught. So 3h naught and so on and so forth. So in other words, ito is j h naught. So this is psi sa function of position, and yung potential nyo, okay, ay meron ding, so halimbawa ito yung shape ng potential. So i-discretize nyo pa rin yan. Okay, so this is this is h naught, this is 2h naught, this is 3h naught, okay. And then somewhere here, nandiyan yung JH naught. Okay. So kaya dito, discretize din yung BJ. Okay. At saka yung wave function nyo ay discretized. Okay. So this actually is a matrix, okay, which we can write as this. Ang kagandahan dito is that itong term na ito ay yung diagonal elements ng matrix. Okay. Yeah. At itong term na ito ay yung off-diagonal elements. Okay, dito sa baba. Kasi itong term ito ay yung next na adjacent na off-diagonal elements. Okay. If you add a tawag dito, if the boundary conditions are periodic, may dadadag kayo ng term dito. So negative u1 at saka negative u1. Okay. So the only thing left to do here is to diagonalize. Okay, and diagonalization means na actually this is diagonalization kasi E is the wave number. Diba? So if you have a matrix which you want to diagonalize, then you multiply it by lambda times I, okay, and then you equate that to 0. Okay, so in this case, ito yung H at yung lambda yung eigenvalues ninyo. And this is just the identity matrix. Okay. Okay. Yeah. Okay. So kunin niyo lang yung determinant nito. Okay. Then you have then you diagonalize or then you perform the diagonalization. Okay. So yan yung numerical method dito. In MATLAB, I think yung function to diagonalize is called diag. Okay. Now, what I'm going to do is to send you yung MATLAB code. Okay, for solving the infinite potential well. Okay, so pag-aralan niyo yung MATLAB code. Okay, in that code, or actually dalawang files yung isi-send ko sa inyo. Pero yung diagonalization happens in the file na solve SCH. Okay. Schrödinger equation matrix dot. So doon makikita nyo yung kung paano sinet up yung diagonal elements na ito at saka itong off diagonal elements. And then kung paano diniagonalize yung ang tawag dito yung matrix na ito. Okay, para makuha yung eigenvalues at saka yung eigenfunctions. Okay, so if you apply yung square wave potential, okay, then you'll end up with this graph dun sa MATLAB na result or MATLAB na code na ipapadala ko sa inyo. Okay? Okay. Now, ang next na i-discuss natin ay yung current flow. So sinabi natin before na merong current, okay, as a result of yung charges na nagtatravel, okay, at a specific direction. To discuss itong current na ito, we begin with yung natutunan ninyo sa 171. Okay. Ang charge density, okay, ng isang system, okay, is related, or the rate of change of the charge density is related to the divergence, okay, of the current density. Okay, so this is the continuity equation in electromagnetism, okay, for currents. Okay, also recall na for a particle of charge E, okay, yung well, hindi to recall, sorry. In quantum mechanics, yung charge density niyan, okay, is equal to E times yung particle. E times yung probability na makita yung particle. Okay, so this is the probability, and you multiply that probability to the charge to get the to get the charge density. Okay, so to get the charge density. Okay, which means na if we take the derivative with respect to time nung expression na ito, okay, we have E partial with respect to t ng psi star psi. Remember, this is just psi star psi. Okay, so equal to ngayon sa E times psi star partial with respect to t ng psi plus psi partial with respect to t ng psi star. Okay. So, recall, okay, na yung Schrödinger equation natin, time-independent Schrödinger equation is written as partial with respect to t, I bar partial with respect to t ng psi r of t, psi of rt, okay, equal to sa negative h bar squared over 2m del squared plus br, okay, psi of rt is equal to h of rt, h psi of rt. Okay, ang gagawin natin ngayon is, so we already have d dt psi. So ito yung d dt ng psi. Gagawin natin is multiply natin ito, yung expression na yan with psi star. Okay, so we have psi star, okay, ih bar, d dt ng psi. Then meron na tayo nung, ano to, di ba? So this will be equal to negative h bar squared over 2m. Okay, Okay, wait. Gusto ko lang mag-conserve ng space para masulat ko yung dalawang expressions. So negative I, H bar, psi star partial with respect to time ng psi is equal to negative H bar squared over 2m. Okay. Times psi star del squared ng psi, okay, okay, plus psi star v psi. Okay. Then, para makuha naman ito, first, we take the complex conjugate of this expression. Okay. And then we multiply it by psi. Okay. So we have negative IH bar psi, and then yung complex conjugate niyan, okay, which will be equal to negative H bar squared over 2m psi del squared psi star plus psi v hindi del, kundi v psi star. Okay, so now we have these two terms. Okay, i-plug in natin yan ngayon dito at saka dyan to get the time rate of change of the charge. Okay. And what we have now is okay, so what we have now is partial respect to time and charge is equal to negative psi star. Okay. Okay, wait. So, may balikan lang tayong konti, no? Sorry. Ibalikan lang natin itong slide na ito. Kasi ang ginawa natin dito sa second term, okay, ang ginawa natin dito sa second term is actually we took the complex conjugate first, which means na dapat kukunin natin yung ang tawag dito. Teka lang, bakit ito dapat ay positive? So we took the complex conjugate first, kaya dito magkakaroon muna ng negative sign before we multiply the sign. Okay, so we have IH bar size, ano tawag dito? So ibababa natin yun yan, ano? So pag binaba natin yan, so we have H bar over 2m, and then may I ka doon. Okay, tapos may E ka dyan, so maglalagay din tayo ng E dyan. Okay. Then, nung binaba natin yung I, okay, magiging ano siya, negative or positive. Okay. So, positive yan. Then we have, ano yung susunod? Ito. So, psi star del squared psi. Okay. Plus, okay, yung E, of course, and then yung I, H bar. Okay, and then yung psi star V psi. Okay, so yan yung first term. Okay, na ito. Then yung second term is minus EH bar over I 2M. Okay, psi del squared psi star plus or minus E over IH bar psi V psi star. Okay, so what do we end up with? Now, ito at saka ito ay equal lang naman sa isa't isa dahil yung V ay real. Since V is real, then these two are equal. Okay. Pwede natin ilabas kasi yung V. Okay, so ang ibig ko sabihin dyan is psi star V psi star is just V psi star psi. And this is just V. Yeah. Okay. And psi V psi stars, you could just tawag ito V psi star, which is also just equal to that. So magka-cancel silang dalawa. Ang matitira is okay, check lang natin yung signs, no? Sige. So this becomes IEH bar, okay, over 2m, okay, psi star del squared psi minus psi del squared psi star. Okay. I just want to check yung signs kung tama. IH bar and then negative doon. Negative, negative. So pag binaba ito, magiging positive. Okay, and then magiging negative. Okay, magiging positive. And then magiging negative ulit. Okay. Okay. Okay, sorry. Pag binaba ito, positive pa rin siya. Pero pag nilagay mo sa taas, magiging negative. Tama. So kaya negative times negative. Okay, sige. Tama na yung signs dito. Okay, so IEH bar over 2m. Okay, now, we can write this as this. Okay, so divergence of psi star del psi minus psi del psi star. And from here, from this, we see that this is equal to negative del dot J. So what we have is yung current density is equal to this. Okay. So yung current density niyan is equal to negative IEH bar over 2m times psi star del psi minus psi del psi star. Okay, or in one dimension, we write negative IEH bar for 2m psi star of x partial with respect to x ng psi of x minus psi of x partial with respect to x ng psi star of x. Okay, now itong derivation na ito requires na yung potential ay dapat real. Okay, so yun yung isang tawag dito, assumption dito. Okay, now let's apply yung na derive natin na eigenfunctions dun sa infinite well na potential dito sa nakuha natin expression for the current density. Okay, so if you recall, yung eigenfunction natin is 2 over L square root sine pi over L x plus L over 2 exponential negative I1 over t. Okay, and then yung ating eigenvalue is h bar omega 1 is equal to h bar squared pi squared 2ml squared. Okay, kung natataka kayo kung saan galing itong L over 2 na ito, this was derived from problem 3.6 na kung saan yung potential is tawag dito, 0 between potential is 0 between 0 and L imbis na negative L over 2 kung saan yung ginamit natin na derivation dito. But actually doesn't really matter. So we can, if you want, we can use this. Diba? Para hindi kayo nalilito. So sin k sub n x, diba? And yung k sub n is n, k sub n x is n pi. So k sub n is equal to n pi over x, actually L, okay, n pi over L. Okay, so papalitan lang natin ito ng k sub n, itong k sub n ng n pi, okay, over L. Okay, so and then syempre multiply natin to by exponential negative I omega sub n t, include yung time, so include natin yun, i-plug in natin yan ngayon dito sa ating expression. Okay, so psi star of x partial with respect to ng ground state, no? Psi 1 of x minus psi 1 of x partial with respect to x ng psi 1 star of x. Okay, pag kinuha niyo yung complex conjugate nito, so psi 1 of xt is just the same as psi 1 of xt. Kasi nga, hindi, meron ka ng, meron ka ng wave function. Sige, susulat natin. Negative IE h bar over 2m psi 1 star. So we have, pwede na natin i-factor out yung 2 over L. Okay, may 2 over L ka dyan, then may square root of 2 over L ka dyan, then may square root of 2 over L ka rin dito, so 2 over L na lang siya. Then psi 1 of x, so we have a sine n pi over L, okay, of x times exponential I omega sub nt, okay, partial derivative with respect to x ng psi 1. Okay, so anong partial derivative niyan? Ng cosine, ng sine is cosine. Lagyan natin ng coefficients. N pi over L. Cosine n pi over L x. Okay, so yan yun. Tapos may exponential negative I omega sub nt. Okay, nando doon. Okay, minus psi 1 of x. So, again, nando doon yung 2 over L. Then sine n pi over L x. Tapos exponential negative I omega sub nt. And then yung derivative ng complex conjugate. So, ang complex conjugate nito is positive lang ito. This is still n pi over L times cosine n pi over L x tas exponential positive I omega sub n t. Okay. Itong mga to ay magka-cancel or they will be equal to 1. And kung titignan nyo mabuti, this is sine pi cosine n pi. Sine pi over Lx cosine n pi over Lx. May coefficients ka dito na common. So this actually cancels each other out. Okay, and yung j sub x dyan is equal to 0. Okay? So, by using itong tawag dito, ground state na wave function, the ground state wave function in itself does not carry current. Okay? Does not form a standing wave. And the reason for that is pag nag-move ka ng isang direction, tapos nag-reflect yun of the opposite direction, okay? Mag-cancel lang siya. Okay. Makikita natin yan dito sa graph. Okay. Itong graph na ito, yung kulay blue dito. Okay. Okay. Pag nag-reflect yan, okay, dun sa barrier, ganito yung magiging reflection niya. Okay. And it will just cancel, okay, with the so itong forward moving na ganyan, then will just cancel with that. Okay. Sorry, hindi ganun dapat yung depiction kasi ito yung standing wave. Yan na yung na-form. Okay, pero ang sinasabi ko dyan is kung meron kang cosine function, okay, that describes yung wave function, or sine function that describes this wave function, it will just cancel pag nag-reflect sila sa isa't isa. Okay? Okay, so, syempre, tatanungin mo ngayon, bakit ka pa rin meron current? If Jx is equal to 0, saan galing yung current? I mean, how is energy transported, di ba, from one barrier to the other? Okay, energy is transported, okay, by not due to a single wave, but due to multiple waves interacting with each other. And pag sinabi multiple waves, ground state interacting with the first excited state. Okay, and so we're talking about superposition of waves. So what I mean is we use psi of xt, okay, 1 over square root of 2, psi 1 of xt plus psi 2 of xt. So this is a superposition of psi of the ground state and the first excited state. Okay, and if we add that, okay, if we use that, okay, here, so psi of xt is equal to 1 over square root of 2 psi 1 of xt plus psi 2 of xt. Okay. If we plug that in dun sa ating expression na ito, okay, what we'll end up with is j of x is equal to negative 2e pi h bar over ml squared times cosine ng pi over lx cosine ng 2 pi over lx plus 1/2 sine ng pi over lx times sine ng 2 pi over lx. Then we have the sine omega 2 minus omega 1 times t. Okay, so now we see na hindi na siya 0. So yung current is carried by the superposition of bound states. Okay. Okay. So that's when you have current. Okay. Because yung states na yun na nag-interact sa isa't isa. Furthermore, yung current has an oscillatory dependence. So nag-oscillate sila. Time dependence. Okay? So, yung frequency ng oscillation ng current, okay, is equal to the difference, okay, between the frequencies of the two eigenstates. Okay? So nag-move sila back and forth at the frequency that is the difference of the frequencies of each eigenstate. Okay, for a traveling wave, okay, ano bang example ng traveling wave? Yung light, diba, is a traveling wave. And we describe yung wave function niya as exponential kx, ikx minus omega t. Diba? And we have this j sub x equal to negative I eh bar over 2m psi star of x d dx ng psi of x minus psi of x partial with respect to, partial pala to, psi star of x. Okay, and if you plug that in there, ito, plug natin dyan dito. Okay, we end up with exponential ikx, ik exponential ikx negative, okay, plus exponential ikx, okay, ik exponential negative ikx. Or this is equal to negative IE over h bar over 2m 2ik or equal to e h bar k over m. Okay. So yan yung current density for a traveling wave. Okay. Na ganyan yung form. Now recall na ang definition ng current density is charge times velocity sa Physics 102. So the charge is E and yung velocity is V sub x. Which means na yung V sub x dito is h bar k over m, or if we write this is mvx h bar k, which is nothing but yung momentum, okay, ng particle. Okay, so yung results natin ay consistent, di ba? Sa isa't isa. Okay, we still get yung original equation for momentum, okay, for a traveling wave. Okay, and we now have this expression for the current density for a traveling wave. Okay, so there's one more thing that we should discuss before we end this meeting. Okay, we discuss now what's called a degeneracy. Okay, degeneracy. Okay. Okay, ano ibig sabihin ng degeneracy? Okay. You have degeneracy when you have number of states that have the same energy eigenvalue, states with the same eigenvalues. Okay, and yung degeneracy na to ay direct consequence often ng symmetry dun sa potential. Okay, so for as an example, we consider tawag dito an infinite potential barrier. So as an example, we consider an infinite potential barrier in 3 dimensions. Okay, so yung potential is 0 for x, y, and z between negative L over 2 tsaka L over 2. So 3 dimensions to. And then yung potential is infinite for negative L over 2 greater than x, y, z, and then greater than L over 2. So outside the boundary. Now yung Hamiltonian dito, we can break down into yung component forms niya. Okay, and the only reason we can do that is if yung potential is also tawag dito ay hindi tawag dito ay hindi dependent sa X, Y, and Z. So we can sort of separate yung potential and into its component form along the X, along the Y, tsaka along the Z. If of course yung potential is only along the X-axis, pero yun yung sa case na to yung potential is 0, so we don't have a problem with that. So we can do tawag dito separation of variables. Okay, so yung wave function natin can then be written as psi x of x, psi y of y, and psi z of z. Okay, and we can treat itong bawat isa sa mga wave functions na to as independent sa isa't isa. Separation of variables, di ba? So this means na yung energy eigenvalues nito is h for psi of x, yung energy eigenvalues ay h bar squared k sub x squared over 2m. Dito naman h bar squared k sub y squared over 2m. And then ito ay h bar squared k z squared over 2m. Okay, and yung total na eigenvalue nila is just the sum of each of those eigenvalues. Okay, so h bar squared over 2m plus kx squared plus ky squared plus kz squared. Okay, na kung saan yung kx ay equal sa nx pi over L, ky is equal to ny pi over L, yung kz ay equal sa nz pi over L. Okay, yung n, x, ny, and z ay non-zero positive integers. Of course, yung ground state, so yung ground state dito is when nx is equal to ny is equal to nz is equal to 1. Okay, so yung E111, okay, E111 okay, ay equal sa 3 h bar squared pi squared over 2 ml squared. Okay. Now, this is the only state sa itong state na to ay may iisa lang na eigenvalue. Okay. Now, since itong n na ito, itong mga n na ito can be iterated between 1, 2, and 3. Okay. So in other words, pwede ako magkaroon ng values ng nx, ny, nz, for example, ng 1, 2, 3. And then pwede kong palitan yan ng 1, 3, 2. Pwede kong palitan ng 2, 1, 3. Pwede kong palitan ng 2, 3, 1, 3, 1, 2, at saka 3, 2, 1. Okay. Ibig sabihin, kahit anong ilagay ko dyan, di ba? So, halimbawa, E1, 2, 3. Okay. So, we have 1 squared. Okay, 1, 2, 3. 1 squared plus 2 squared plus 3 squared. That's 5, 9, 14. 14 h bar squared pi squared over 2 ml squared. Tama, no? 1, 4, 9. 14, okay? And that's the case for any of these states. So, 6 na states yan. Okay, at iisa lang yung kanilang, pare-pareho sila ng eigenvalues. So now we have these, we call these states as degenerate states because they have the same eigenvalues. And this is a six-fold degenerate. Okay, so again, kaya nagkakaroon ng degeneracy of states ay dahil sa symmetry in the potential. So if we reduce or break the level of symmetry, mababawasan din yung degeneracy. Okay. So that's it for today. Okay. Next meeting, we'll discuss a few more examples kung saan natin pwedeng i-apply yung Schrödinger's equation.